has car insurance. Just in case switch over.
Yeah, I might be able to sneak out a little bit early, but the last talk was one that I wanted to see because it's a colleague of mine. So, and it ends right at 5 o'clock. So, I will basically try to find a quiet room on the side and get on Skype and answer any questions. Thursday, I'm not quite sure. I would try to be able to do the same thing. I should be at the airport on Thursday about this time. So I will let you know the time on Thursday. So when you do meet on Tuesday, if at least one person could bring a computer that you guys can Skype with. My Skype name is Eggplant on Ice.
Let's see. Oh, there it is. Okay.
It's up here. Sorry, I know it's a weird one, but it's a nickname.
Interesting.
I think I do have I made one point, I made a more formal, just Aaron Pettit one that was for having more formal interactions. But most of my friends have this one, so this one's the one everybody kind of expects.
Yeah, I have my formal Skype and then my Skype I use with my friends.
You should at least once eat an eggplant on an ice to fit
I have. Well,
Okay,
I've
so you
had
did that.
eggplant on ice.
Okay.
And actually, there's a great picture of me somewhere with an eggplant that they sent out to our camp. So it's like me holding this eggplant up. Yeah, it was pretty funny. Yeah, it's been a nickname for 12 years now or something, 10 years. Okay, and then so yeah, what we're going to do today is take the conservation of momentum, what we sort of came down to at the end. Most of these are going to be slow-flowing fluids, so we actually are going to always assume that acceleration terms go to 0. And I want to kind of run through some different examples. I don't know that we'll get to all of them today. There's some of these are also in your notes. There's also some slight variations in your notes. And then there's two slightly more complicated ones that are in the notes. And there are, I think both of those are in the notes, but there is, there are 2 videos that I put together last year with me going through them on the iPad, and those are linked within those calendar days there. So these are, the idea here is just to give you guys some practice of how to think through what assumptions can we make, what assumptions can we not make right away, what are the effects of a different assumption, because you could have the same system, and then depending on whether you choose assumption A or assumption B, you'll get a different answer. And Neely was asking earlier about how do you know when to make assumptions. In the real world, when you're actually really solving problems like this, it does sometimes come down to your judgment. And as you get to know a system, as a scientist, you'll start to know whether or not is it justifiable for me to assume that there's a sliding boundary on this, or what are the limitations based on past research? What have other people done in terms of this particular assumption? And do I agree with what everyone else has done, or do I want to say, no, I don't agree with this assumption, I'm going to take this different assumption? And we'll try to talk a little bit about what you can use to justify different assumptions in different situations. So the first one, I want to kind of walk through together. And what I did on these, so if you remember on this version of the equation, these three equations that are on all of those pieces of paper, or on most of them, this is already written out, assuming no acceleration. So this is what we ended with on Tuesday is this version where we have the derivatives of the stress plus some force is equal to 0. So initially we're starting here with just the assumption that that there's no acceleration. That doesn't mean that there's not flow or movement. All it means is that the flow is slow enough that the acceleration terms can be very small compared to the stress terms, the stress gradients.
Is that F, does it have an I or a J?
It's a J. No, it should be an I, sorry. So connecting this to what's on the paper in front of you, if you guys have had a chance to read through the notes, you probably will see this. We do have two I's here, but they're in different terms. So we don't sum over those I's. There are J's here in the same term, which means we sum over them. And that's how we end up with this d sigma 1, 1, dx1 plus d sigma 1, 2, dx2 plus d sigma 1, 3, dx3 plus f in the one direction equals 0. So this is saying that the body force is in the same direction as the direction of the normal, which is also related to the sigmas that we're working with here, or the shear forces that we're working to. It's the plane that the shear force, or the direction of the shear force is acting. Do you guys see that? So in all of these cases, we actually have three equations that we're trying to solve simultaneously. So actually, I'm just going to go ahead and write this out so that we can talk through it. Oops. 2, 1, dx1. This is why I printed these out for you, because it's...
Is it standard notation to write FB and not FI?
Not necessarily. FB would just be a body force
right.
in that direction, and I don't know why I put FB here as just being a little more generic. FI is just
more explicit.
What are the directions that are
right.
associated with that? So it's probably better to write the FI, or X, the capital XI is what we were using on Tuesday. And actually probably what I should have done on this is gonna, whoops.
Wouldn't each of these be like plus F1 and then the next one plus F2?
Yes.
And, okay.
Exactly, which I'm just doing right now. So I just saw that that's a better way to write it. This first one we're going to do is this, you have to dig it in there, the cylinder with just a stress applied in this x3 direction. And I'm probably not going to, well, I'll try to write these up as we go, but you guys have that to write. So this is just this one, sigma 3, 3. And for now on these sides, I'm going to say this is a free surface. So the way you approach these, and hopefully you guys have had a chance to look through some examples in the notes, but you just start listing what assumptions you have, and that can start telling you which terms are either 0 or maybe you don't know yet what they are. So if we have a free surface, what does that tell us about the stress on that surface?
There is none.
There is none. And is that true for both normal and shear, or is it just that there's no normal?
Should be for both, right?
Yeah.
Yeah, it's for both. So it does mean that there's no normal and there's no shear. So with that, what can we do here? Which ones can we cross out? Assuming we have sigma, or sorry, 3.
The 2 and the 1. Sigma 2s and sigma 1.
Yeah,
Direction.
if we know that sigma 1, 2 is on that, so we don't have any shear in this direction, we don't have any shear in this direction, we don't have any shear in this direction, we don't have any shear in this direction. So pretty much we can cross out all of our shear. When you write this down in a problem, you want to write down free surface, and you want to tell me that you know that that means 1, 2 equals sigma 1, 3 equals, just write out all the components of stress that you know are 0, so that I know that that's what you specifically know are 0, as compared to knowing that the x's are 0. So we also said that this means the normal stresses are 0. I should switch colors here. Okay, so our shears are all 0. Every time I accidentally hit the bottom of the screen, it's pausing. Be careful. We said the normal stresses were also 0. So that's the sigma 2 and the sigma 1 terms. So we can get rid of the sigma 1 term, we can get rid of the sigma 2 term. Basically, so right now, did we apply, have we talked about applying of body force in this one yet? No, I didn't specify here. So depending on your situation, you may or may not feel like the gravitational force is important. In this case, we're going to start out with it, there not being any gravity. So we'll just, and here you can see already that by our other assumptions, the gravity, basically the body force in the F1 and the F2 direction kind of has to be 0, the way we've set up this problem. So we've already, we can assume that it's 0, but we also have just shown that it has to be 0 if our other assumptions are correct. This F3 is the only one where we're consciously saying, yes, gravity is 0, so we're going to get rid of that. So what are we left with?
I missed. Why did you say gravity is 0? Just for this case.
Problem,
Yeah.
we're going to make
Okay.
that assumption.
Okay. Yep.
We're God in this case.
Yep.
We need
No, that's good.
rid of gravity.
Sigma 3 is a constant.
Yeah.
Sigma 3 is a constant, right? So now we've got a nice solvable equation. We can integrate. Sigma 3 is a constant. That's saying that it has to be a constant all the way through the material in this direction. How do we decide then what the value of sigma 3 is? Not a trick question.
Take a real world measurement.
So yeah, in some case
Stress.
we might take the road measurement. I also told you that there is a sigma 3 applied to the top and bottom. So that's our boundary condition, right? So we've got sigma 3. So we've decided that sigma 3 is a constant. To figure out what that constant is, we can follow that constant value all the way to a known point. And our known point here is what we've decided is on our boundary. So that's our applied force. So it equals our given force. We might measure it if we have a measurement. Usually that means we measure it on the boundary or something like that. But this is where we bring in those boundary conditions, in this case we have one boundary condition that helps us figure out what that C is. So what makes this goes much more smoothly, and so you don't make mistakes along the way, is that you actually go through those steps carefully. Even if it seems easy to just say, oh, well, then sigma 3,3 is our answer. If you don't consciously think, okay, sigma 3,3 is a constant, and I know it's that constant because I know what it is on the boundary, I know what it is at this one point, then, you know, you can make mistakes if you try to jump too many steps ahead of yourself. So I really like to see you guys work through these, even if they seem simple, work through the steps of saying, yes, it's a constant, okay, what is the constant? Well, then what happens? Is this thing deforming? What else, what do we need to know to figure that out?
The properties of the material.
The properties of the material. Yes. So now we have our body, we're applying our sigma 3,3. Our stress tensor, sigma ij, we've just figured out is 0, 0, 0, 0, 0, 0, 0, 0, negative sigma 3,3, because it's a compressive stress, the way I drew these arrows.
I mean, it's bulging in the middle.
So it's probably bulging because we put no stress on the sides. How do we figure that out? How much is it bulging? Let's think about our conservation of, just conceptually think about the conservation of mass. If you did take a cylinder and you squeezed it in one dimension by a certain amount, say delta L, so we squeeze it by a little bit, delta L, how much do you expect it to bulge out on the sides?
Proportional
Yeah.
to L, depending on the geometry of the shape.
So it's a circle. Is it going to bulge out delta L in each direction?
No.
No,
No,
less
I mean-
than delta L. But our stresses here are 0. So how do we figure out how much it's bulging? If we have 0 stress, how do we relate 0 stress to a finite amount of strain that we know should be there?
Oh, it will be negative stresses. No, that doesn't make sense.
So you
So
said-
what would this, so if we know that it's squeezing down our strain, so let's estimate our, what we
so
think.
assuming the pipe is not giving an opposite force to opposite stress, is that the assumption?
Yeah, so we assumed it was a free surface, so it's free to do whatever it wants. It's got no stress. Nothing is holding it in,
Okay.
right? Because that is another version of the
Actually,
assumption.
it is
we can
a-
make.
There is an expansive stress.
There
'cause
will-
it is
yeah, there will
pushing
be.
out.
There is an expansive stress, right? But we just said it was 0. So anybody dig in their memory
we
of what
said-
they read in the notes? Does anyone remember there is a stress that's causing that deformation, but how do we get that stress from this stress? There's a slightly different name for it. Do you guys? Does anyone remember?
Does it start with a D?
Yes.
Deviatoric stress?
Deviatoric stress. So the deviatoric stress is what's doing the work. What we figured out was the total stress. Does anyone remember the relationship between the deviatoric stress and the total stress? We didn't actually go through this in detail in class, so I realized this one.
Something like
Difference
1/2
between-
parentheses. Or is that
Oh, you're going towards the strain, connecting it with the strain, which is
It's like the stress without shear.
those are the principal stresses. that is slightly different. So the deviatoric stress, the symbol is tau, and it's equal to the total stress minus something.
Minus
Okay.
the principal. No.
No. It's basically minus sort of an average stress. Because remember, you were bringing this up before, that it's the differences in stresses that cause deformation, not
Mhm.
necessarily just the total stresses.
Yeah, that's what I was thinking when I said principal. I was thinking lambda, because
Right, this is
that's.
not lambda, this is P for pressure.
But the delta is what I was thinking of.
Oh yeah, the delta,
Yes. The diagonal.
the diagonal, yeah, so,
That's what I was saying. Principal.
right. Yeah, so it's in that equation as well. So yeah, you guys are remembering all sorts of bits of this, but this is why I kind of wanted to go through this. So basically what we're saying is that what's causing the deformation is not the overall total stress, but it's the stress that's different than the average stress over the whole thing. And that average stress is basically our pressure. The pressure is the trace of the stress tensor divided by 3, so that's an average stress.
But so I'm interested from why are we subtracting specifically the trace and not the rest of the stress on that matrix, and why is only why are you going for the trace? Is what I feel like I'm close to thinking of understanding that
Yeah.
component, but
So, yeah, that's a good question. So do you guys remember what the invariants of the stress tensor are? Or of any tensor? What are the 3
First.
invariants?
Then
What's the
Uh,
first
the
invariant?
first one
The
is
sum of the-
trace,
The
the
first
sum.
one is the trace.
right,
So the trace is the same no matter how you rotate it.
right,
The trace is also those normal stresses.
right,
And so what we're interested in, we can, whatever stress tensor I give you, I can rotate it around such that there are always zeros
mm-hmm.
here, right?
Mhm,
So
mhm, mhm.
so you can always find the principal directions, which
Right.
is what you were thinking about. Basically, this is also the sum of the principal, or 1/3 the sum of the principal stresses.
Mhm,
So
mhm.
you could say this is lambda 1 plus lambda 2 plus lambda 3.
Right.
So even if there were shears over here,
Mm-hmm. Mm-hmm.
the trace should still be the same as in the case where there are zeros there. It's just a different rotation.
I understand.
So this trace version, the 1/3 of the trace,
Mhm.
is a version of a pressure. It's sort of an average pressure that gives us an invariant that doesn't depend on the orientation that we're looking. And if we subtract that out, it gives us the stress that's actually doing the work. This is like your swimming pool. If it's just sitting there, the pressure at any point is just the pressure and there's no movement. But if you tilt the surface of the swimming pool, there will be a difference, a slight difference in the stress tensor from point A to point B. But the movement doesn't really, it depends more on that difference in the stress at those points than on the actual pressure term that you might feel if you were in the swimming pool. So it's the tilt that's driving the flow of a lake and turning it into a river, basically. So we're always going to be, when we want to know deformations, we always are going to look to this deviatoric stress. Sometimes we can get there directly, sometimes we need to go to this first and then subtract out the pressure.
And so that will always be negative, right? Oh, I don't know what case. I mean,
Not necessarily.
No.
It might be. It's always going to be. So this stress, tau, is always going to have some relationship with our strain or our strain rate, depending on the material properties. In this case, we squeezed it vertically, so that is negative, but we have a positive dV torque stress in this direction. So it's not necessarily always negative, because we have to have what's causing the thing to bulge is an outward dV torque stress that's pushing that material outward.
Because actually those eigenvalues are actually 0 is what we defined it initially, no?
Here there's 0, 0, and
Gamma 1, gamma
3,
2, gamma 3 are 0.
So in
No,
this particular case,
two-
let's walk
two
through
is-
it the rest of the way here. So what is our P here? Let me get rid of this for the moment. P equals the trace, negative sigma 3, 3 divided by 3. So if we subtract P, our tau equals 0 minus sigma 3, 3 over 3, 0, oops, 0 minus a negative, sorry.
Yeah, it's plus.
So plus, and then 0 plus sigma 3, 3 over 3. And here we have sigma 3, 3 minus, minus sigma 3, 3 plus sigma 3, 3 over 3. That's all scribbled in there. Which means that our tau equals sigma 3, 3, I'm just going to call it sigma, because I'm tired of writing 3s. Sigma over 3, sigma over 3, and negative 2/3 sigma.
Sigma on the top there.
Oh, sorry, sigma on the top. Do you guys see that? So now if I tell you that this
What this means, the sum of the invariant for this case means that it's not going anywhere, right?
right, so the trace of this deviatoric stress tensor will always be 0
Meaning nothing is moving anywhere as a sum,
as a sum.
right?
Right. Conservation of mass, continuity in the strain and the strain rate tensors.
And actually there's
If
conservation of
this
momentum,
trace is always 0, and our tau is related to strain or strain rate under normal circumstances, the traces of the strain and strain rate tensor are always 0. And that's our conservation of mass that we derived the other day.
And momentum, no? Is that also
Well, conservation of momentum is
okay,
this,
is
this
applied.
whole system that we got there.
right.
Okay.
Yeah, okay.
So yeah, now we have tau ij is equal to sigma over 3, sigma over 3, negative sigma, negative
2/3.
2 sigma over 3. If the strain is equal to some elasticity times the stress, you could figure out what the strains are. Right? Pretty easy. Our strain rate tensor is going to be E sigma over 3, E sigma over 3, and negative 2 E sigma over 3. And that, so this is double, so if you squeeze it by delta L, then you're going to get half that in each direction. So you squeeze it and not delta L in this way, you get half bulging out that way and half bulging out this way. in the strain version, not in the net total length, I should say, because that's all relative. Because if you have a longer one, so if you have a really long one, you squeeze it by a certain fixed amount, that gets spread out over the whole thing, so your actual L change might be tiny, but the strain will be, because this is smaller, right? So the delta L over L, if you have a long L this way and a short L this way, then your delta L in this direction, it's the strain that's half. So if we say this is in the one direction, and that equals the strain, it's not equal to. In the other direction, delta L2 over L2 is equal to 1/2 of this. If we have a little tiny L2, then our delta L2 is also going to be really tiny, but it's still going to be half of this ratio. So this doesn't tell you the absolute change in the size. It tells you the relative change in the size, because that mass is spread out over the entire length of our tube. Does that make sense?
So the negative sign means it is getting smaller 2 times compared to the
Yes, it's extending outward.
extending outwards.
Yes. This is assuming an elastic material whose density does not change in the process.
And the object orientation is a cylinder. Like, how do we determine the 1 and 2 directions? Does it involve with the sine and cosine?
It's going to end up.
Because
It's going to be symmetric all the way around. So if the 1 and the 2 are the same, then they're all principal directions, so they all will have the same.
You already gave the orientation by saying that the top and the bottom is 3, so.
Right, so then the 1 and the 2,
Oh,
I have to think about that. It might actually get spread out a little differently when it's cylindrical.
if it was a box, yeah, it's easier to
Yeah,
think of.
what?
yeah, it does get distributed a little bit differently as a cylinder. That's right. Thank you for bringing that up.
Wouldn't it be even for a cylinder?
It'll be even all the way around, but
Yeah, but you have, corners that you would have to account for in the cylinder because it's just like, it's all
Yeah.
round.
Yeah.
It's not just side to
yeah,
side,
I
side to
think
side.
we would end up converting this to cylindrical coordinates.
Right,
Yeah.
yeah.
So we would end up with
Yeah.
the same idea, but we'd just be doing it in cylindrical coordinates, and I'd have to think about whether or not we'd still be conserving mass in the end.
You saying it might not be that ratio? Or
Well, the
ratio.
amount, the actual amount, it should be, I can't remember if it's still E sigma over 3 if we're doing it cylindrically symmetric. I'd have to look that up, I forget. It's close though, but the same concept applies. You can write these equations in cylindrical coordinates and get there directly. So if we have a material, this is where you get into some cool material properties. If you have a material that has what's called the Poisson's ratio actually is about kind of how it effectively changes density under situations like this. But because right now we're conserving mass assuming density is constant. But there are materials for which you squeeze it in one direction and it doesn't exactly, volume-wise, it doesn't stay the exact same. And a good one, there's a lot of them out there. I mean, if it's foam or something that has like squishable properties, you can end up with a different amount of net strain because you're conserving mass, not necessarily volume in some of these cases. And there's actually some materials like fresh fallen snow, if you squeeze it in one direction, it actually has a tendency to squeeze itself in horizontally because of the way the snow crystals are they're interacting between each other, so it has what we call a negative Poisson's ratio. This has a Poisson's ratio of 1/2, meaning we squeeze it this way and it bulges 1/2 in the other two directions. A cork in a wine bottle is another funky material where it's got a little bit different one. When you shear it, so if you twist it, it sucks itself in, which is why they use it for wine bottles. And actually, I think if you compress it, it also sucks itself in. So you can get it back in the wine bottle. Like, try doing what we just did, this cork-shaped thing, and getting it back into a wine bottle.
I could bring some wine and we could test this out.
Yes, we could do some testing of different materials.
Tuesday, we're going to have some in-class
So it's the
experiments,
properties
guys.
of the cork, or it's the air? It's the air.
It's the properties of the cork, the material cork. So if you just did what we did, you try to stick this back into the cork, into the wine bottle, you push, it bulges out.
Yeah, I've attempted this. This doesn't work
It's
as well.
not going to go.
Turn it upside down, it goes back in.
I see it.
So you guys know.
Student problem coming on with the added mass of the of your opener.
Yes,
As
yeah,
well
yes, of the opener.
as well as the stresses of twisting.
A little bit of, yeah. So this is why cork is a popular material and why it's not so easy to find materials, because we can get a cork back into a wine bottle. If you just chose a random material, you might be able to get it out of the bottle, but you won't be able to get back in. It's also why twisting makes it, those ones that you twist in, and then if you try to pull straight up, it's a lot harder than if you give it a little twist while you pull up.
Just wiggle,
Because-
just wiggle, 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 come on.
No, I tell you, try the twist.
Twisting,
Yeah.
no, that's
Try the
genius.
twist. Because if you just pull up, cork is the exact opposite in the sense if you squeeze it, and if you twist it, it narrows itself down. But if you pull straight up, it actually bulges out a little bit, which is why it's so hard to get them out by simply pulling.
So what did you learn in geophysics today? Well, how to open wine
How to
easier
properly
and
open
how to
wine
close it again to preserve the wine.
It's so not
It's a
intuitive.
good day in geophysics.
This
This is
concept.
why materials are so cool. Material properties are just cool. Non-normal linear material properties.
Slightly unrelated. So in your notes, you said near the bottom there was this melting silly putty looking thing that you said we could do in class if we wanted to.
Oh,
We should do
bring
that.
silly putty in.
That-
Yes, should have brought silly putty in.
It looked like it was melting-ish though. Did you heat it up or is that how that?
No, if you just set silly putty.
Oh, it'll just slowly. Okay, so that's what it was. All right, I gotcha.
Yeah, yeah. I can go grab some silly putty. Or I can give you some to watch next week. Okay, so the second one is actually, actually, really quickly, I just want to do one more thing with this version. So we made the free surface assumption. But Ale brought up the point that what if it's not a free surface? What if we have something holding it in?
Then we know what is the. We know what sigma 2 force would actually be to make the system.
How would you find it?
You actually just the same. We know what pressure is being.
We don't know. So I give you sigma 3,3. I only tell you how much is being applied at the surface. But and then I just tell you that it's not changing its shape.
But you know, it's 2/3 is applied to the side. So in order for the system to be in equilibrium, you need to have 2/3 from the outside in.
Right, but can you work through that from the beginning? What are you doing in that case?
Are you saying sigma 1 also has a?
Yeah.
Okay, I was just
Some,
making sure.
but we
Yeah,
don't know.
yeah.
We don't know.
Yeah,
what
yeah. I was
these
just
are.
making sure that you're pushing it on all sides.
You're
to keep
assuming
it
there's
from deforming.
nothing. It's zero. It goes the
What
whole
is
path.
it we're assuming? I'm just trying to, you're right, I'm just trying to get you to
W-
state
we're-
it more explicitly. What is it we're assuming then? I
We're
don't-
assuming the walls are not putting any pressure back into the
And how can you write that mathematically?
sigma 2 and sigma 1 are equal to 0.
No? What do you, say again what you're saying. The walls are,
Exerting are not exerting any pressure into the cylinder, well, into the box.
no, I tell you that the thing isn't deforming in that direction.
So okay, oh I see.
It's,
So
we
I
don't
mean,
know what the stress is.
I see. So
I don't know how
si-
much stress to apply, so
so that we're saying the opposite forces are equal. That's what you're trying to get to.
no, I just told you that it's not deforming.
I mean, so at time 0, the opposite of forces are equal to 0. No?
Does anybody jump in and help?
Sure.
The
So
wall is not moving. What's our mathematical assumption there?
Is it negative 3, 3?
That there's no change in.
Sigma 2, 2? Wouldn't it have to be the
So I give
opposite
you
of...
the stress here, this is our
yeah, but
sigma 3.
the stress is divided between sigma 1, 1 and
Oh,
2, 2,
yeah.
right?
Yes.
So
But what's our assumption on the wall? I'm telling you it's not deforming. How can you write that down mathematically?
strain equals 0?
Strain equals 0. Sigma 1, 1 equals
Yeah,
sigma 2, 2 equals 0.
I was thinking, yes.
So
I was
you're
thinking- I
jumping-
was thinking
you're
into
jumping
stress,
ahead,
but yeah,
yes,
yeah.
you're jumping ahead, and this is why
Okay.
I want you to go through these steps carefully. So
Yeah.
the assumption here
Strain is-
is that we don't know what the stress is, but we do know that it's not deforming, which tells us that these components of our strain tensor. So we kind of have to work from both directions, because before we just did is we started with the stress and we said, okay, we know what our stress is here, and I gave you sigma 3, 3. We decided, and you could walk through this by canceling out all of those equations. We actually don't know what sigma 2, 2 and sigma 1, 1 are in this case. These are question marks. We might be able to say that their derivatives are 0, but we don't know their values. So in order to connect this with this, what do we need to do now?
Excuse me, are you using the same coordinate system, like 1, 1, 2, 2? Because
Yeah, this is supposed to be a 3, 3. It's just
Yeah.
poorly written. Yeah.
okay.
So 1, 2, 3. Same coordinate system, same everything, except now I tell you that the sides, they're no longer a free surface. I'm telling you that they're not deforming at all.
So it's not deforming in what direction? I mean, like
In
upside
any
down
direction.
or? Oh, I need.
Except the top. The
Oh,
sigma
except the
3,
top.
3. Sigma 3, 3 is still there. Same,
Okay.
same. It's just the sides are fixed and they're not
Okay, so
deforming.
it's not deforming.
Yeah.
Do we know if the density is changing? Is that still constant
Yeah.
in this case?
Density is still constant.
Did we say anywhere here that the strain on a 3-3 was changing? What did we say about that?
We haven't said anything about that.
Oh, interesting.
So what did we do? So before you had this and you had those zeros in, what was the next step we did?
Subtract from the trace, the average.
The average trace, right?
average
Which is
trace.
that pressure.
Yeah.
Right. So if we take that step and tau ij, our p is equal to sigma 1 plus sigma 2, which are unknown values, plus our sigma. Let's make this a giant Q or something. That's the applied one. That's the one we know. But sigma 1 and sigma 2 are still unknown. So we can still walk through these steps, just keeping those as unknowns. We've decided, if we decide that the derivatives of those are 0, so in our original equation that's here, we could say that the derivatives are 0. but we don't know the values. So we know they're a constant, we just don't know their values. So our question marks are sigma 1, sigma 2, they're question marks, but we can say they're a constant. I think that's a pretty good assumption in this case. Because it's the same material all the way through, it's a nice geometry, and we know that there's nothing really to change it spatially. So we can walk through the same thing we just did, keeping this equation there, so it's hard to all write that all out, but we'd say sigma 1 minus RP, sigma 2 minus RP, and then our giant Q minus RP, and this is our known value. Now we can say, well, sigma 1 minus P is equal to our elasticity times sigma 1, 1, but what is sigma 1, 1? I'm sorry, what is epsilon 1, 1?
0.
0. So if there's no deformation in this direction, then there's no deviatoric stress, because the deviatoric stress always goes with the deformation. That does not say that there's no total stress in the system. It's just the deviatoric stress is 0. What's the trace of our strain tensor or deviatoric stress tensor? Conservation of mass?
0.
0. So if this term is 0 because we said this had to be 0, if this term is 0 because we said this had to be 0, what does that tell us about what's happening in that third dimension?
They're equal.
Canceling.
Zero.
Canceling each other.
They're canceling each other, yeah.
0, 0, what does that
But
have?
Q equals to P, is what you're saying.
You keep jumping ahead like 3 steps.
Are you pointing at it?
I'm pointing at it. What is that value of that Q minus P? What does that equal?
It equals 0.
It equals 0. Yes, then Q equals P. So
Okay.
you just your brain's working too fast. So if these have to be 0, then this has to be 0. And what does that tell us about deformation in that third dimension?
0.
It's 0. So if we are conserving mass, we are not having density change, we're not allowing it to expand in that third dimension, then even though we're applying a stress to the top, it's not deforming. So its deviatoric stress is 0 in that case. We can still have this overall total stress, it's just not doing anything. Got it? Question?
Typically, if I say typically your tube is not, doesn't have it cannot apply the same stress across the entire tube, so that's why it'll have the bulging in the center. Right?
Well, in this idealized case, we are applying the same stress at the top and bottom.
Well, I'm saying the
And-
sides. So typically the sides are not. If you have a typical tin
In the
can.
real world, yes, you would end up with a bulge that looks like this because of edge effects here.
Yes. Yeah. So you need to say infinite.
So you could, yes,
Cylinder.
you can, and that's one of our other problems here is the squared version that I wrote up, where I said the edges are far, far away.
Yeah.
You land far, far away.
Okay.
So is this starting to make sense? So there are more examples. I just wanted to go through this first one really slowly. It took us a while. Hopefully that was useful. So you can have assumptions that are the stress value. You can have assumptions that are the stress gradients. You can have assumptions that are the strains. You can have assumptions that are the strain rates. You can have assumptions that are the velocities, if it's a fluid that's moving. So, and those are often boundary conditions or assumptions about simplified geometry or infinite geometry. You can make these kind of assumptions. So the next one I want you guys each to just kind of jot down. We're going to do this one. It looks like this.
Is there a difference between page 3 and 4? Is 3 and 4 the same?
This is not
Wait.
page 4.
Yeah, this is
Not
page 4.
But
That's
4
page
the same,
8.
right?
Page 8. There we go.
Yeah,
Page
page 8.
So here I told you that the edges are far away, and I also want to tell you that actually rather than sigma 3,3 as a constant, I'm going to change it and make it gravity. So sigma 3,3 is there, but it's in that direction, but it's gravity being applied.
So top
So
and
only
bottom.
the top.
Sigma 3,3 is unknown. I mean, it's, yeah, you could say that it's only being applied to the top, but it's just gravity being applied.
Okay.
And this is on some fixed, and edges far away.
You would say it's sigma g over the surface area at the top of the box, right? Because g is acceleration. Or how do you...
G is an acceleration. The gravity, the force, then ends up being the mass times the acceleration.
But
which
then
in
the
this case is
stress would be divided by the area of the surface of the box. Is that how you would?
well, this body force is already in dimensions of pressure, of stress gradients. So it's a.
We
so
typically do this in
is-
force. I guess maybe I missed. We would typically do this in newtons and not in
We're doing
in,
this
in pressure.
So the units of this equation. What are the units of the first part of this equation? What's the unit of a stress gradient?
I would think it would be under pressure. Is what I.
Well, pressure and stress have the same units. What are the units of a pressure gradient? Spatial pressure gradient.
So it's pressure divided by the length.
The-
or pressure divided by
Divided by
meter.
a distance. Yeah.
Right.
So it's
Yeah. Yeah.
pascals
Over meter.
per meter.
Right. So it's.
And all of these are at I mean, this is a force. I mean, we use it as a body force.
Right.
We have our mass, which is really the integral of the density, but we got rid of the integral.
Right. Right.
So this is more like a volume
Mass.
force acting at a
Yeah.
point. But if you figure out density, the units of density times acceleration, you get back to
My
this.
mistake. I was thinking of the surface instead of volume. Okay, I see
Yeah,
what
so
I
this
see.
is acting through the
Yeah,
whole
yeah,
thing.
yeah, yeah. Of course. Yeah.
And so just start making some notes for yourself on what assumptions you want to make. And I'm actually going to we're going to get some of that stuff pretty soon. Thanks so much. Next week.
Do we know anything about the edges and the boundaries
That's
there?
like, what's the
other
difference
than-
between free surface and just assuming they're really far away?
She made the
Like, would they
assumption
react-
earlier. Now she's just more explicit. I think.
Well, like, do they act the same way?
As a free surface, like, is it going to be 0?
Like,
I think it's free surface.
yeah, like,
Okay, so it's free to
regardless of if
expand.
they're far away, what's
It's
there?
far away.
Direction one and two
The
is
fact that
pretty
it's far
certain.
away, that means that the
It is a free surface?
Yeah.
It still
One and
reacts?
two.
Okay.
The different when it's far away, it means that all that surface is going to expand the same. If they were close, it would expand differently.
Yeah, I mean, it doesn't matter too much because
Right.
strain is not dependent on.
And that P or rho there, she said that's mass.
That's
Density.
density times gravity.
Okay.
Yeah, which yeah, it is. Didn't catch that.
So let's go. This is our model, only it doesn't have its edges very far away.
Use our imagination. Been a lot of putty.
Okay. Assumption. Annie, what's one assumption that you think we should make?
Uniform density.
Uniform density, good. Rho is a constant. Joshua,
Can I say it's a free surface as the assumption?
what's the free surface?
So there is no normal, shear forces along the 1 and 2 sides.
Well, but we said edges are far, far away. So, do we know that it's a free surface or not? What if that free surface is 1,000,000 miles away? Does that help us much?
Or the strain in the in the direction 3 is 0 because it's
Okay, so we can say that the top has free surface. That we
so
know.
the top has
So there's a free surface at the top.
so
So that means sigma. Yeah. So I put. It had that written on there, right? The 1, 2, and 3.
It only has
No.
3.
Oh, it only has 3. I made it this way, 1, 2, and 3. It doesn't matter. It just ends up changing your math when you look at the. But anyway, sigma 3, 3 is 0 because it's a free surface.
Mhm.
What else? So we have no normal stress at the top, and what else for free surface?
no shear forces.
No shear forces. So sigma 1, 3,
1, 3.
and
You mean 3, 1?
And 3, 1, because they're equal, so there's symmetry
Okay.
there.
And 2, 3.
Sigma 2, 3. And what
Yeah.
is it? Does it tell us anything about? Does that free surface tell us anything about the 1, 2 direction? Or the 1, 2 shear?
It is not 0. They are not 0.
We don't. It doesn't tell us anything. It
Or it
doesn't
does-
give us any information because that
Yeah.
the free surface is only the 3 surface.
Mhm.
So we can only say something about 3s when we say that that's a free surface. So we're going to get rid of this, get rid of this, get rid of this.
Just-
What is-
Yeah.
So what's the
I'm
exact
gonna go
definition
back
of free
for a second.
surface?
That's a good question.
Yeah.
Go back for a second. We're going to do this in 2 steps. Because what that is telling us that this is true at x3 equals 0. So it only tells us what those stresses are on that boundary. Right?
So the definition of free surface is it's
It has no normal and no shear on that surface, which might just be at that point. So do we know yet if it's a free surface here, does that really, what does that tell us about what's happening at the bottom? Is it also 0 at the bottom with gravity?
No.
Do we know that? No, because we know that there's a gravitational stress inside there, so we know that it can't be 0. In the other, so this is a boundary condition that we'll keep this in mind. We're not sure what it's going to get us yet. And if we combine it with some other assumptions, we might then be able to do a little bit more.
So gravity doesn't affect the top of this little cube thing here.
Yeah, there's
So-
nothing, well, there's no, it's air pressure.
Yeah.
And so you could put air pressure in there. But yeah, gravity won't affect the top
Gotcha.
because there's nothing above it to
Yeah.
push down for the gravity to be working on.
How about the bottom? The bottom of the silly
The
putty.
bottom
Or
is
the
sitting
box.
on
oh, I see how we're
a
doing this.
table.
Hmm.
What do we know about that?
Well, the gravity is pushing it down because it has masses. It has mass. Object.
So
So
could
we consider that.
at the bottom we could say, what
Yeah.
would you say?
Some stress, like
And what would be the, do you know what the magnitude of that stress is?
the force divided by the area. So it's
Well, for gravitational stress at depth, you guys just did this in your,
the Rho G
How much-
H.
yeah, so we can put that down. It actually will come, that one will come out of our solution as well.
Yeah.
But the stress at the bottom is just going to be the weight of the column of silly putty above it.
Oh.
But
Those
yeah,
are
so
mine.
we can write
Yours?
these down.
Yes.
So what's another one? Lindsay.
I was trying to keep them.
I don't know.
What about the edges far away assumption that I gave you? What is that? How do we, what might that tell us mathematically?
Are we assuming that the H is a lot smaller than the width?
Yeah, so H is much smaller than some L. But what might that tell us about what then is happening in that 1 and the 2 direction?
The deviatoric stress is 0.
It's very small.
Not necessarily, but what is, you're on the right track. If H is much smaller than L and the edges are far away and we're considering this a uniform constant density material, Can we generate any gradients of anything in that? If it's infinite going off in that direction, and it's the same from this point to this point, and this point to this point, and this point to this point, and
So-
that goes on to infinity,
You get a really small number.
that tells us that the derivatives, all derivatives in those infinite directions are 0. 'Cause you can't have infinity if you have some constant, some change in that direction. If it changes in that direction, then it's not infinite, because you have stuff happening. But if it's infinite in that direction, then your gradients in that direction are 0.
Mathematically, you can divide by infinity. That's what we're saying. Saying we divide by infinity, and therefore the
And
value is
therefore
small.
it's 0. Yeah.
Is it
It
actually
all goes
considered
to
0? Okay. Oh.
1 divided by infinity would be 0.
Okay.
'Cause
What do you mean by edges? Like, is that these edges or these edges? It's two edges, because
Oh, yeah, okay.
it's
good.
not clear.
Yes,
right?
no, it's not clear. I meant the sides.
Oh, so it's flat. It becomes like. Okay.
I mean, we're basically doing the silly putty, but the edges, the sides are far, far away.
The sides are far away. Okay.
The next
That-
problem should be the silly putty concept. Or
Will do. So now with this, I can be like, okay, that's something I can do something with right now. I see this, I can go through and say, okay, all derivatives in these two directions are 0. Yay! Get rid of that, 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 get rid of that. Done. That makes me happy. Because I just got rid of a bunch of stuff. The next assumption I think that we could make. What do you think? What's your,
The body forces in the F1 and F2 directions are 0.
good. That's a very good one. So assumption 5 is F1
I
equals
think I'll write
F2
that down.
equals 0.
Why? Is that
Gravity acts
Gravity.
in the vertical
Yep.
direction.
okay? Gotcha. Just testing you.
And so now we're down to a few equations. It's looking a little more manageable. Can we say, we said here that sigma 3 at the bottom is rho GH. Is there anything we can say about these?
I mean, it's supposed to be.
Andrew?
Wait, sorry, which those two?
I'm going around in the circle.
Okay.
just
Well-
so I've noticed.
We can say that those, or we can put it back into our equation. We know that then the partial derivative of sigma 1,3 with respect to 3 and 2,3 with respect to 3 are both equal to 0 because the force there is equal to 0. So putting
The derivatives
sigma,
are equal to 0.
yeah, the derivative of sigma plus f, then
So what does that tell us about the value of this?
so it at least has to be constant.
So it has to be constant. And any ideas on what could help us figure out the value of that? So if it has to be constant,
So it also has to be 1,3 and 2,3 have to be equal to 3,1 and 3,2 respectively.
right. So yeah, these have to be equal. But here we
But we-
only knew that the derivative was constant, so that doesn't help us
Yeah.
know that the value, what the value is. So this is the stress in
Yeah, the there's no
this direction or this direction.
yeah there are no forces acting any way other than down in the vertically. So there's no shear forces happening, and the edges where any weird oddities might occur are very far away. So we're not really worried about those in our
Exactly.
setup.
So in this case, we do have this nice geometry. Stuff is far away. We're not applying any shear forces to the boundaries. So there's no way for, if we're not applying any shear forces to the boundaries, and those shear forces, this is telling us they have to be constant, that kind of implies that there are no shear forces then, so those have to be 0. Yeah.
I mean, we already made the assumption that number 2, like the shear 1, 3, and 2, 3 is already 0 because of the free surface.
Right, because the free surface on the third free surface is 0. Yeah, so that connects it straight to, like, that's saying that we're not applying any shear. Yeah, perfect. Yep. So you can refer back to this one and say, hey, this is 0, therefore these have to be 0 too. So we're left with this guy. F3 is negative rho g. This is where it always, I think that's positive rho g actually, where this is written.
So at the top on number 2,
Actually,
you
we-
also had
Yeah.
sigma 3 equals 0. Is that just
Sigma 3 equals 0 where?
is it just at the top then? So at the
The
bottom.
free surface is just at the top,
And not
so
the
that only exists at the top. The reason this applied is because we said that this derivative had to be 0, which meant that sigma 1, 3 is a constant everywhere. Sigma 1, 3 is a constant everywhere. We know it at one point. So therefore, we know its value here, and we know that it's constant everywhere, which means that we know its value everywhere now. Sigma 3, we know that it's 0 at the surface, but we don't know its value everywhere, and all we know is that this relationship tells us what its derivative is. Do you see the difference
Yeah.
there?
Yeah.
So you have to remember that a boundary condition is just that, at the boundary. And you have to apply it carefully.
So,
No, sorry. I mean,
so the derivative of 3 is equal on x3 is equal to rho g, and we can integrate along x3.
This is, so sigma 3 now equals negative rho g x3 plus c.
You could do you could define like some like height, which is down from the surface, and do a definite integral and say it's equal to minus rho g h,
So yeah, so sigma
or
3
little h.
at x equals 0, because the way this is part of the reason I had drawn the 0 in
Or
my box.
solve it
is,
for like that.
Yeah, so this is the 3, 1, 2, 3 in the box that I had when I did this on my scribbles. The reason that I did that meant that we know that sigma 3 is 0 at x equals 0. And yes, then we can say that x3, we have some h, so x3, so we can also then say sigma 3 at x equals h is equal to rho g h, and we can replace that x3 by the equation that x3 equals, well, x in the case that because I started at 0 and I'm going down, from 0 to h. But if we want to know it at any point, then we do want to keep the x3 in there, because it's only the integral if we're going to go, if we're integrating it all the way through. So our sigma ij now equals 0, 0, 0, 0, 0, 0, 0, 0, negative rho g x3 plus c. But since we've decided that it's a free surface at the top, that c is 0. If we were also applying a stress at the top, then we can add that in and then our C would not be 0. I'll just get rid of this. So we have a nice equation for sigma now, or a nice tensor for sigma now. We can now do the same. We can go do the same process with our sigmas, figure out the tau, the deviatoric stress, and our strain rates. In this case, it's more of a fluid because it's our silly putty. And there are two assumptions that we can, the same like with the last one, we can have two assumptions in this dimension. So we already know it's infinite, but our two assumptions are, one, to allow gravitational spreading. So even though the sides are far away, we can still say, well, they're far away, but they still can spread out farther. And that's what's happening here. So if we allow for gravitational spreading, what does that look like mathematically? And then our other option is no gravitational spreading. If we allow for gravitational spreading,
so that'd be a. Do we have to know the material to know whether it's viscous or elastic?
this one we'll say is viscous. But so yeah, we do, and that's why I put the strain rate here. But you could do the same thing with an elastic. If you wanted to go elastic. So what was the assumption we just made about allowing for deformation of our blob sideways in the last problem?
You said that there was no deformation.
Well,
No.
the first time we did it,
Right.
we said that it was a free surface on those sides,
Right.
And that told us that the stress was 0.
So, and we said that the
Actually,
strain was
actually-
0.
Hmm?
And then she said that the strain was 0.
That was in the second one.
Yeah,
The
Right.
second one.
So the second one where we allowed no deformation in that horizontal.
Right.
We said the strain was 0.
Mhm.
Are we not saying it for this one?
Well, we have
Not
two
yet.
assumptions. We can either allow for gravitational spreading or we can not allow gravitational spreading.
Okay.
So if we don't allow gravitational spreading, that's like
Yes.
the second one.
Okay.
So here, if we don't allow gravitational spreading, we're going to say that our strain rates have to be 0.
Mm-hmm.
And I should go back because we actually don't know all of these. I want to be clear on this. I wrote it this way, and that was in haste, and this is why I should be very careful in the future. From our assumptions, we figured this one out. We actually did not necessarily figure these out. We did decide there were 0 shear stresses.
Mm-hmm.
So we're back to this case where we have question marks here,
Right.
and we just know this. Okay? So now, our decision is either no gravitational spreading, which means there's no strain rate, and if there's no strain rate, then we have to have no deviatoric stresses. So there's no deformation happening, which means that the total stress tensor is there, it's just not doing anything. So there is no trace of our deviatoric stress tensor. If we allow for gravitational spreading, that is actually saying that the 1, 1 and the 2, 2 are 0. Here we're saying that 1, 1, 2, 2 equals question mark. But we're saying that epsilon dot 1, 1 equals epsilon dot 2, 2 equals 0. This is that assumption we're making. So it's the same assumption as we made before when we were holding our thing in. So no gravitational spreading. Here, if we're allowing gravitational spreading, we're saying that there is no stress, external stress kind of being applied to hold everything together. So these stresses are 0, but that means that we have to have some deviatoric stress to balance our sigma 3, 3. Because the trace of this ends up being 0 to conserve mass. If it's, because we assumed also the density was 0. So this is where these values might be different, but their traces have to be 0 to conserve mass. This is what we know. So again, you can go in multiple directions, but in both cases, you can fill in the blanks with just a little bit of math. Does that make sense? So, all of the rest of these problems are pretty similar. I'm going to put a couple of them I have my notes on because we're running out of time. I just want to talk a little bit about some of just want to kind of review our common assumptions. So free surface we've talked a lot about. And that's no normal or shear on that surface at that point. 2, we also talked about density or other material properties being constant. So that's a good one. 3, we talked about infinite in some directions. And if it's infinite in that direction, that means that the derivatives, if it's infinite in the x1 direction, all the derivatives in the x1 direction have to be 0, because that means there's no change happening. No change in that direction. It doesn't tell us about the magnitudes in that direction. It just tells us that there's no change in that direction. What else? A general one is that if you're not, under most geometries, if you're not applying a shear stress, it's kind of hard to generate shear within a system. Like gravity doesn't really generate shears in a system if, in a system like this, because gravity, unless you've got something else going on. So you can often say if you don't have shear being applied at the edges and the geometry is simple enough that it's hard to generate shears inside. I mean, it's hard to generate shears under certain conditions. You can, in some places, and I should take that back. Gravity does apply in one direction, but there are cases where you can generate shears with gravity. I just lied. Were there any others that we came up with?
Body forces.
Yeah, we might assume something about the body forces, the direction, the magnitude. And then 5, if we have a known stress at the boundary or known strain or strain rate. So that's another one that we know. You have to be careful with these that you're not jumping to conclusions because you think that it has no strain rate. So you want to be careful to just figure out what you really know versus what you think is probably happening. Then the other ones that I
Wait,
really...
sorry, what was that conditional? You said if there's a known stress at the boundary or a known strain, then...
So if you really do know it...
Okay, then there
So
is...
if you
then
know
it's
you're
true.
applying a certain magnitude, then yes. Or if you know that it's not deforming in that dimensions, yes. But if you just are like, well, it seems like it's not, shouldn't be deforming in that dimension, I would say don't jump to that yet. You always want to hold off and make as few assumptions as possible as you work through and see if you can solve it without that next assumption. So as you cross these off, you'll get to the point of like, well, can I solve this given what I have in front of me now? And if it's a simple enough equation that you just have to integrate, then there's no reason to jump to that next conclusion. You might be right, your instinct might be right, but you should be careful of applying instinctive boundary conditions versus ones that you actually know. A few others that we didn't quite get to in these examples. With fluids in particular, the no slip boundary condition, what that's saying is that a particular boundary can have a normal force, so you can have a normal stress, but you can't, you can have you have normal stress and your shear stress will prevent any motion. This isn't necessarily saying anything about the normal. You can still have regular normal stresses on this, but your shear stress means that your velocity there is 0. So this actually isn't, the no slip isn't always a stress condition. It's a velocity condition.
So it's just saying like it's pushing against velocity in like the opposite direction of the velocity of whatever's there.
Yeah, so it's reacting to that motion. And this is it's the reason that water is still at the edges of rivers. It's a very common, like in general we assume that when a fluid hits a solid, the molecules closest to the boundary stick to the boundary. And so the velocity right there at the boundary is 0. You could also have the opposite, and that's a slippery boundary. So this one is subtly different than a free surface where it can still have a normal stress, but all shear stresses have to be 0. You may not know the velocity at that boundary, but you do know that the shear stresses are 0.
So would that mean that in the 2 examples we've done, the shears, there were slippery boundaries? Since our shear stresses were 0, or does that not?
Yes.
So we did have slippery boundaries.
We did at the bottom of the one that we were allowing. If we allowed...
But so a free surface would not be considered the same thing as a slippery boundary?
It's a free surface is slippery boundary with an extra no normal stress.
Oh, okay.
Because you could say that between the air and the fluid,
Yeah.
it's a slippery boundary.
Yeah, okay.
And those were the most common ones, actually. When you get to having some fluid flowing down a slope, your gravity is going to show up in two different equations. So there's a component of gravity in the downward, and this is like number,
Page 3.
yeah, it's page 3. In this one, it actually is not, it's almost like what we just did, but all we're doing is tilting it. So a lot of the same assumptions apply, we're tilting it, and therefore gravity will show up in two of our equations instead of just one. So, and a lot, like I said, a lot of these are worked out in your notes. And for example, the no slip with a fluid flowing down a slope will end up, the velocity will end up being curved like this. And depending on your situation, the strain rate is usually constant through there. And you have a curved velocity. This is where we get the squared that we had in the river flow before. I told you that. But this is all worked out in your notes. So if you remember what we've talked about today, we've just gone to the point of the strain rates. But then our strain rates are related to our velocities, because the velocity in the one direction, dx2, but the velocities, the strain rates are derivatives of the velocities. And then, nicely, what you were remembering is for a shear strain rate, so if we do have a velocity as a boundary condition, we sort of have to walk through.
Is it a fume hood alarm?
That's probably
The
test for today.
Oh, yeah.
It says they were going to test
Yeah.
today.
I guess we're probably failing the emergency
Yeah.
test.
Yeah.
Shut them out.
There's a window.
So yeah, you can have, if you have velocity boundary conditions, you have to kind of keep that unknown into your equation all the way through until you get to velocities. Then you stick in what you know, and then you can work backwards as you need to get back to stresses or velocities. Does that make sense?
It's probably the alarm system thing
Probably.
too.
Yeah.
Everything is.
It's always probably one.
Um, So several more of these are walked through in the notes. There's at least two more complicated ones in the videos from last year. But it's the same process, and you just sort of carefully walk through them step by step.
I think it is the emergency system.
Yeah.
'Cause I didn't know that they called people.
I knew they'd send text.
Yeah, I knew
Yeah,
they get
they-
text. They send
sent an
text too.
email.
See, at my undergrad, you had to sign up for this. You couldn't. They didn't just automatically.
Facebook
send
gave them
these
the
things.
information.
Yeah. You're just like, oh, we're gonna sign you up.
I had one question about the computing assignment, real quick. In the you're asking us to find, just sort of like take estimated values for like stress and viscosity and things. You also wanted an estimated idea for strain in the Earth, at least in the relaxation model it was. I was wondering what, like, I was trying to just think of a good, like, trying to figure out what, a value of
What a good
strain in
estimate.
one dimension that's sort of like, just to help define our function.
Well,
and-
think about plate tectonic deformations that you know are out there. Because that is a strain, or there's a movement.
Okay, because the values we had been giving were more like in the mantle.
So
It
look up
seemed to be-
how fast things flow in the mantle.
Google is not always
So
useful.
is it, and this is what I was talking with Matt about, so if we're looking at how fast something's moving in the mantle, is that not a strain rate?
That could be a strain rate, yes. But
But we can use that
so
value.
you could also, I mean, the mantle has both elastic and viscous. And I'm kind of leaving this, like there's a lot of different ways. You can look at the strain rates in the mantle. You can look at like lithospheric deformation. I mean, I don't know that I told you to only look in the mantle.
No, you just said
Well,
give
when it
estimates
said
of
for,
Earth.
Earth-like
for
mantle.
the Earth.
But the only things we can find are mantle values, really, it seems.
Mantle values, so there's
Yeah.
nothing about lithospheric deformation in papers, and I'm sure that some researchers, I'm not, you can look farther than Google. There is such a thing as journal articles and stuff if you really want to, and you might have to go to Google Scholar and then
Yeah, that's
actually
what
look
I've been
into
looking
the-
at is Google Scholar.
Look into the papers, and look, like there are, what happens in an earthquake? What are, the last time the San Andreas Fault went, what were some of the stresses going on? What was the strain? Was there a net strain? So there's a lot of different ways you can look at Earth-like values. Just come up with a consistent set of values. So given this particular situation, I expect stresses around here, the elasticity of the crust is this, and I expect some strains or strain rates in these particular things. So either mantle, crust, kind of ice. I mean, I asked you to find ice, I think, separately, but yeah, so.